Hi there, welcome to section 7.6. This is the last section in this chapter, and it has to do with exponents. It's going to be a lot of calculator work. Please make sure you bring your calculator. And it's formula work, so we're just going to need to know how to use the formulas and then put stuff in there. So we've got three formulas: exponential growth, exponential decay, and compound interest. So notice this first one is exponential growth. So let's talk about this formula. Let's write down what everything means, and then let's use it. So first of all, the y that is the equal sign is your final amount. If we're going to figure out exponential growth, that means we start with something, it gets bigger and bigger and bigger, and then we've got a final amount that we're wondering about. A is our starting or initial amount, so we'll put that on the outside of those parentheses. The R is the rate of change. It's going to be the only percent in the problem, but you have to turn the percent into a decimal. So that's really important. That's why I typed that in there. And last but not least, the T is time in years. So you have to be really careful. Make sure you're looking at years, not in days or weeks or months, but in years. So let's use this formula and let's do an example. It says down here, the population question. In 2008, the town of Flat Creek had a population of about 280,000 people and a growth rate of 8.85% per year. Write an equation to represent the population of Flat Creek since 2008. A lot of times they're going to break the problems up into two parts like this. Let's figure out what we've got. So first of all, the population, 280,000 people. That is our starting amount, right? So that is going to go into the A. A growth rate of 0.85% per year. It's the only percent in our problem. That's going to go in for the R. But we're going to make it into a decimal. Remember, when you turn a percent into a decimal, you scooch the decimal point back 2 places, which would make it 0.0085. The decimal started here, and I moved it back 2 places. 0.0085, important. It doesn't tell us the final amount, and it also doesn't tell us the time, so we're going to keep t as a variable. We don't know that. So in other words, it just wants you to fill in things. So we're going to put y equals. In place of the A, 280,000 people, parentheses, 1 plus something. What is that R going to be? I probably didn't leave enough room for it, but 0.0085. And we said t we do not know, so I'm going to leave that as an exponent on the outside of that problem. The reason we leave that is because part B is going to say, according to your equation, what will be the population of Flat Creek in the year 2018? So in other words, we're going to use that and we're going to fill in the rest of the information. So I'm going to rewrite everything except for the t. Notice how that's a plus inside that parentheses. I'm pointing that out now for a reason. Here's the question that I've got to ask you. We're going to put a t in that spot right there. We're going to actually put a number. But what do we put? Do we put 2018 there? When did we start keeping track of the population according to the problem? 2008, right? When are we wondering about what the population will be? 2018. So what will be our time in years based on starting with 2008 going to 2018? We're going to put a 10 in that problem. Now this is where your calculator work gets important. So here's what you should do. You should start with doing the parentheses because that's what PEMDAS tells us to do. So go to your calculator, do 1 plus 0.0085. Take your exponent button, because that's the next thing in order of operations, and take that number to the 10th power. Then multiply, because that's the next thing in order of operations, multiply whatever you get for that decimal weird answer by 280,000. So I'm going to end up with a final answer, and we'll go through this in class too, of 304,731. I rounded that to the nearest person because it's a decimal. So that's why I didn't get, I'll get a crazy decimal for that, but I'm just not going to. So we have to follow order of operations, which means that I had to do the parentheses first. I had to do the 10th power exponent next, and then I had to finish by multiplying by 280,000. Try the math, make sure you get the same answer, but we need to, just kind of get that taken care of, but also figure out where to put things into the formulas. So let's talk about exponential decay. So exponential decay, notice, first of all, let me highlight. There we go. That. Notice inside the formula, it's y equals a times the difference of 1 minus r to the t power. I've got to subtract. Doesn't it make sense that in decay we would subtract? The last one in growth we would add. So one way to keep them straight. Otherwise, this is an identical formula. So we know that y is our final amount. We know that a, there it is our initial or starting amount. We know that r is the rate of change. The only percent is in the problem, but we're going to turn that into a decimal. And we know that t is the time in years. So these two formulas are actually really easy to remember. Once you remember one, you remember the other because it's either add or subtract for growth or decay. So our example problem, it says during an economic recession, a charitable organization found that its donations dropped by 1.1% per year. Before the recession, the donations were 390,000. Write an equation to represent their donations since the beginning of the recession. So we're going to do the same thing. We've got a part A where we're going to set it up, a part B where we're going to do the math. So where does this 1.1 go in for? That's going to be our R, right? And when we turn it into a decimal, when we move that decimal point back 2 places, it looks like it's going to be a 0.011. Don't forget to do that. That'll screw up all your problem. Where's this 390,000 going to go in place of? That's going to be our starting amount, or our A. It doesn't tell us a time yet, so we're just going to keep the t as a variable. So I'm going to have a y equals A, 390,000, parenthesis, 1 minus, because it's decay, it's subtracting. Clue word for this, dropped, decayed, decreased, getting smaller. Anything that says it's getting smaller says we should use decay. So 1 minus a 0.011, and that will all be to the t power because we don't know t yet. However, it says in part B to estimate the amount of the donations 5 years after the start of the recession. So now I know what I'm going to use for the t. No tricks in this one because it just flat out says 5 years, right? So let's go to our calculators. Well, let's write down our equation first. 0.011 to the 5th power. So go to your calculators, follow order of operations, start with parentheses, 1 minus 0.011. Raise that answer to the 5th power. Take that number, so you're never going to clear out your calculator, round anything. You're just going to keep adding on or multiplying on to the answer that you had previously. When I do that math, I ended up with a $369,016.74. Since it's money, I went to the nearest penny. The last one was people. We can't really have like 0.74 of a person, so I went to the nearest whole person. So $369,016.74. Notice it's less than what we started because it was a decrease, a drop, a decay. All right, last formula is compound interest. This one's a little bit tricky, so we're going to talk about this in class, but I want to make sure that you have the formula. Notice the formula's got a lot more happening here. So a little bit different terminology, but A is the current amount. Compound interest is going to be things like loans or putting money into a bank or a savings account or saving for college or taking out a car loan or a house loan, those kinds of things. So the current amount would be how much money you have now or how much money you have to pay or things like that. P is the starting amount, also known as the principal, which is why it's used a P for that. This N, this is pointing to the N down on the bottom. This is the number, hence the N, the number of times compounded each year. So that is the N that is on the bottom. That's why I typed it on the bottom. Be careful, make sure that yours is pointing to the right thing. Up here, the R is the rate, again, as a decimal, so that's the same. And then notice our exponent is N times T. So the N is going to be repeated. We already did the number of times compounded each year, and we know that T is the time in years. So there's some common compound times down here. We're going to talk about this in class, but how many times a year they're adding interest? So if it's annually, they just add interest once a year, right? One time. If it's monthly, every month they add interest, how many times a year would they put interest on that? So let's just stick with the annual. Whoops, for a second. Try that again. All right, so the problem down here has Paige. When Paige was born, her grandparents invested $1,000 in a fixed rate. Let me scooch that up for a second. In a fixed rate savings account at a rate of 7% compounded annually. Paige will receive the money when she turns 18 to help with her college expenses. What amount of money will Paige receive from the investment? So here's what we need to figure out first of all. I'm going to scooch this down for a second so I can see the formula. There we go. Here are the things we need to know. A is what we're looking for, right? How much will she have at the end? I need to know what P is going to be, the starting amount or the principal. Well, what was the starting amount? $1,000. I'm going to need to know the rate. What does it say the rate? The only percentage in this problem is right here, rate. If we turn 7% into a decimal, what would that be? 0.07. We need to know the N, the number of times compounded each year. Here is your clue word. Annually, what does that mean? So N equals how many times a year? 1. And we need to know the time in years. It's telling us in this problem. They put the money in when she was born. When does she get the money out? When she's 18. So what will our time be? 18 years. So let's use that formula. Let's set this up. So we've got A equals the principal, $1,000, parentheses. And then inside those parentheses, we've got 1 plus. Notice it's growing, so it's adding. And we've got to have our R over N. So what is our rate? 0.07 over the number of times compounded each year, we said was 1. And that's all going to be raised to the N times T power. So 1 times 18. I highly recommend that you do that exponent math either mentally or on the side, because when we go to do this on the calculator, you don't want too many things happening. I know that 1 times 18 is 18. So here we go. Calculators. Do the division inside the parentheses. So take a 0.07 divided by 1, which is an easy problem in this case. Add 1. Raise that to the 18th power, because I did the mental math. Take that answer and times by 1,000. If you're struggling with the calculator part, make sure you say something in class and we'll look at that. When I do that calculator math, I ended up with $3,379.33. Again, money, so I raised that, or so I rounded it to the nearest penny. So not too shabby. Her grandparents start out with 1,000. She walks away with $3,379.33. We could take that, right? That's a long time to wait for it, though. So that's what compound interest does. This one's the trickiest of the formulas because of the R over N part. So we'll make sure that we talk about that and we'll do some examples together in class. Here's what I would like you to do for the last two pieces. Summarize in your own words, what is this lesson about? What do you see with these formulas that we're using? And I know it's a bit wordy. However, if you look at the bottom part, it says just to write the equation to represent the population of Johnson City since 2005. I'm telling you that your T is what we do not know. So you're just going to do it like those two part A's. You're just going to have a T as a variable. It says the population of Johnson City in 2005 was 25,000. Since then, the population has grown at an average rate of 3.2% per year. Well, if the population has grown, are you going to use the exponential growth or the exponential decay formula? So make sure when you do your formula, you've got yourself a plus inside those parentheses. That's it for section 7.6 and the end of chapter 7. Go back, rewatch anything that you might need to because we will be reviewing and looking at a test at this sometime in the near future. Have a great day. We'll see you next time.